The last thing that we're going to talk about in physics is fission and fusion of a nucleus. So, fission is when you actually bombard a nucleus with a really fast-moving neutron. So remember we talked about the Hadron Collider. This is what we do as well. So we're splitting a nucleus by smashing a neutron into it. And when this happens, you actually cause the nucleus of the element to split apart, okay? And really at first there's like this intermediate situation where the neutron sort of becomes embedded in the nucleus and then it explodes apart. So at the end, you have to have this conservation of nucleons. So we start with a really large, heavy atom, so like uranium. And uranium is has 92 protons and a mass of 234. And if we were to smash a neutron into it, remember the proton number would stay the same, but we would add, and so that's why you see this uranium 235, like intermediate. And then it breaks apart, it decomposes, and it smashes, and most often it'll smash apart into barium and krypton. So I want you to notice here that how we write this is you've got barium. Barium is a mass of, or a proton number of 56 and a mass of 141. And krypton is 36 with a mass of 92. So here we need to have all the masses add up. And as you can tell, like this mass is not going to add to what these numbers represent. So there must be some neutrons that were released. This adds to 233, okay? This adds to 92. So the 92 is good, but we've got 233. And over here, note, we've got 235 total nucleons. So in order to show the conservation of the nucleons, there's also 2 neutrons that are released. So this shows the form or the chemical reaction for a nuclear fission reaction. And then the last is nuclear fusion. So nuclear fusion is when you have 2 very small nuclei and you combine them to form a heavier nucleus. And the heavier nucleus is lighter than the sum parts of the total. So there must be some conservation of mass. So we do have some subatomic particles coming off, and there's a huge amount of energy that is then lost as a result of this type of reaction. Right now, we can harness, we use nuclear power plants and we harness energy from fission. We have not been able to harness energy from fusion. This happens in stars, it happens in the sun, but we haven't been able to harness the energy that's created in a fusion reaction. So here you can see it. This is where it's slamming 2 hydrogen atoms together, and based on what isotope they are, they're given names. So deuterium is hydrogen with 1 proton and 1 neutron. Tritium is hydrogen with 2 neutrons and a proton. And essentially you smash them together. They fuse, but it's a little unstable, so it releases a neutron, a huge amount of energy, and then we've fused to form a helium atom. So if you look at the form over here, we start with hydrogen that is the isotope 2, so that's the deuterium. We smash it with the hydrogen that is tritium, and then in the end you end up with a helium, which is a 2,4. In order to conserve the mass or the number of nucleons, then we know 1 neutron is released, and we typically list below the amount of energy that was released, and so here it shows that energy in mega electron volts. So that is nuclear fission and nuclear fusion. So make sure that at this point now you can identify the equations for fusion, fission, but also alpha, beta, and gamma decay.